to solve the second problem of electricity and magnetism first partial that says like this. Using Coulomb's law, calculate the electric field vector in component form due to a ring with a uniform charge Q at a point P located at a distance Z along the vertical axis perpendicular to the ring that passes through its center. So we will have here the ring and here we have the z-axis, here we have the y-axis, and here we have, well, this way we have the xy axis. Here we have a point P that exerts a force, an electric force due to the ring. So we take this small piece of the ring that we will call dq that has a distance, a length ds. This dq will create an electric field dE that we will decompose in components, and we know that this angle is theta, so here we will also have theta, so this component will be equal to the dE, that is this one, times the cosine of theta. Okay, and we know that from the point P to the y-axis we have a distance c. Once we know this, all this stuff, we know that our little part of the charge has a linear density according to the linear dimension, that is ds. So the electric field that we call dE, because it's the part, will be equal to Coulomb's constant times this part that will be equal to the linear density times ds, that is this part, over the distance, that is this part, square. So this part is z, and we will have a radius r, capital R. So here we will have c squared plus r, but as it is the square root square, we cancel it. So once we know this, we can see that as the ring is over the x and the y axis, the force due to both axes will be the same. So the components of the electric field are cancelled, but the component in the z-axis are not cancelled. So we will have an electric field in z that will be equal to the electric field times the cosine of theta. That was the one we set it in here. So once we established this part, we can start working with this with the electric field. So the electric field here of the cosine of theta will be equal to this part that we established here, the Coulomb's constant times the z, because right, this part, the cosine of theta, we established that the cosine of theta, it's equal, as we see it in here, theta here, it's equal to the cosine of theta will be equal to z, that it's the adjacent caret, over r, that is our hypotenuse, and so it's z over our hypotenuse. So that's why we will have cosine of theta, it's z, and then our ds over r, but our r, we mentioned that was our relation between the z and the r, the capital R, that is our radius. So we will obtain here that our r will be exactly z squared. Here we are missing a square, r squared, and this is half because it's the square root. Okay, so here we will obtain that this part it's equal to z squared plus r squared, and if we multiply this part and this part, we will obtain here 3 halves. Okay, so once we are approaching to the value of the dE cosine of theta, that it's the value of the component in z that we are looking for, we can establish that the electric field it's equal to the integral of dE, that is the part of the electric field that we are looking for in this small part, but we want to integrate it to obtain the electric field of all the ring. So yeah, as we integrate it, we will obtain that it's the integral of dE, but it's the cosine of theta, because that's what we are working with in here. So this will be equal to, as we said it here, this part of lambda. Here I missed lambda over this part is exactly written as the same, z squared plus r3, and this is time the derivative, the integral of ds, that is here. But we know that the integral of ds is integrating this part throughout all the ring. So if we integrate all the ring, we will obtain that it's the circumference of all the ring. So the circumference of all the ring is equal to 2 pi r. So this part will be equal, so all this part will be equal to